Section 1 Introduction. In the past 10 years, the field of machine learning has been largely influenced by the trend of training increasingly larger networks, often referred to as the stack more layers approach. The definition of a large network has changed, moving from models with 100 million parameters to those with hundreds of billions. This shift has made the computational costs of training such networks too high for most research groups. Despite this, the need to train models with significantly more parameters than training examples is not well understood from a theoretical perspective. Other scaling methods, such as more efficient scaling optima, retrieval-augmented models, and simply training smaller models for a longer period, have presented new and intriguing trade-offs. However, these methods do not help us understand why we need larger models, and they rarely make the training of these models more accessible. For instance, training retro requires a complex training setup and infrastructure capable of quickly searching over trillions of tokens, while training Llama 6B still requires hundreds of GPUs. In contrast, methods like zero-redundancy optimizers, 16-bit training, 8-bit inference, and parameter-efficient fine-tuning, PEFT, have been instrumental in making large models more accessible. Specifically, PEFT methods have made it possible to fine-tune billion-scale language or diffusion models on consumer hardware. This leads us to question, can these methods also be beneficial for pre-training? Pre-training is the step that allows for small modifications to the network to adapt it to new tasks. It has been shown that the rank of the changes needed to learn a task decreases the more you pre-train the network. Moreover, several studies have shown the simplicity of features extracted and used by language and vision models, along with their low intrinsic dimensionality. For example, attention patterns in transformers often exhibit a small rank, which has been successfully used to develop more efficient variants of attention. Furthermore, overparameterization is not necessary for training. The lottery ticket hypothesis empirically shows that during initialization, or early in training, there exist subnetworks, winning tickets, that when trained separately reach the performance of the full network. In this study, we focus on low-rank training techniques and introduce ReLoRA, which uses low-rank updates to train a high-rank network. We empirically show that ReLoRA performs a high-rank update and achieves performance similar to regular neural network training. The components of ReLoRA include initial full-rank training of the neural network, LoRA training, restarts, a jagged learning rate schedule, and partial optimizer resets. We evaluate ReLoRA on transformer language models up to 350 M parameters. We chose to focus on autoregressive language modeling, as this approach has demonstrated its universality in most of the applications of neural networks. Finally, we observe that the efficiency of ReLoRA increases with model size, making it a viable option for efficient training of multi-billion parameter networks. Each experiment in this study has used no more than 8 GPU days of compute. Section Summary. In recent years, the trend in machine learning has been to train larger and larger networks, but the computational costs associated with training such networks have become prohibitive. Alternative approaches, such as more compute-efficient scaling and training smaller models for longer, have offered interesting trade-offs but do not address the need for overparameterized models or democratize their training. However, techniques like zero-redundancy optimizers and parameter-efficient fine-tuning have made large models more accessible. In this study, we introduce ReLoRA, a low-rank training technique that achieves performance similar to regular neural network training. ReLoRA is particularly efficient for training multi-billion parameter networks and requires no more than 8 GPU days of compute for each experiment. Section 2 Related Work. We're going to discuss some related work in the field, focusing on two main areas: the balance between scaling and efficiency, and the concept of parameter-efficient fine-tuning. Firstly, let's talk about scaling versus efficiency. The connection between overparameterization, which is the use of more parameters than necessary, and the trainability and generalization of neural networks is a topic that has been widely researched. However, it's still not fully understood. What we do know is that there's a strong correlation between the size of a network and its performance, which is consistent across different types of data. This suggests that overparameterization can be beneficial, and it's why we often see the use of large, resource-heavy neural networks. However, the lottery ticket hypothesis proposes that we could potentially reduce overparameterization. It suggests that there are smaller subnetworks within the larger network that, if identified early in the training process, could be trained to perform just as well as the full network. Next, let's look at parameter-efficient fine-tuning. Research has shown that pre-training can limit the amount of change needed to the network, or its intrinsic dimensionality, when learning a new task. In other words, larger networks or networks that have been pre-trained with more data need fewer adjustments to learn something new. This is why parameter-efficient fine-tuning methods have been successful, and it's also what has driven the development of low-rank fine-tuning methods like LoRA and Compactor. Finally, we'll touch on the topic of low-rank neural network training. This approach has been used in the context of CNN compression, regularization, and efficient training. However, most of these methods are either specific to CNNs, don't scale well, or haven't been tested on large transformers with hundreds of millions of parameters. These large transformers could greatly benefit from efficient training. While transformers have been shown to have a low rank internal dimensionality and representations, research has shown that the low rank of key and query projections in multi-head attention can limit the performance of transformers. Our own experiments have also shown that low-rank transformers perform significantly worse compared to the full-rank baseline and ReLoRA. Section summary. The relationship between overparameterization and neural network trainability and generalization is still not fully understood, but scaling laws show that larger networks can significantly improve performance across different tasks. However, the lottery ticket hypothesis suggests that it is possible to minimize overparameterization by identifying subnetworks that can achieve the same performance as the full network. Pre-training reduces the amount of change needed for fine-tuning, explaining the success of parameter-efficient methods. While low-rank training has been explored in CNNs, it has not been extensively evaluated on large transformers, which can greatly benefit from efficient training. Recent studies show that the low rank of key and query projections in multi-head attention limits the performance of transformers. Section 3 Method. Let's delve into our method by first revisiting some basic linear algebra. Specifically, we're interested in the rank of the sum of two matrices. The rank of the sum of two matrices, A and B, is less than or equal to the sum of their individual ranks. This limit on the rank of the sum is exact. For a matrix A, if its rank is less than its dimension, there exists another matrix B, with rank less than its dimension, such that the sum of these two matrices has a higher rank than either A or B individually. We aim to utilize this property to develop a flexible and efficient training method. We begin with LoRA, a method that efficiently fine-tunes parameters based on the concept of low-rank updates. LoRA can be applied to any linear operation parameterized through a matrix W with m rows and n columns. Specifically, LoRA breaks down the weight update, delta W, into a low-rank product of two matrices, W_A and W_B, where a fixed scaling factor, usually 1 R, is applied. In practice, LoRA is typically implemented by introducing new trainable parameters W_A and W_B, which can be merged back into the original parameters after training. Even though the total update over the training period could have a higher rank than any of the individual matrices, LoRA implementations are limited by the rank R, which is the maximum rank of the product of W_A and W_B. If we could restart LoRA, meaning we merge W_A and W_B during training and reset their values, we could increase the total rank of the update. Repeating this process multiple times results in the total neural network update being the sum of all the individual updates. However, implementing restarts is not straightforward and requires certain modifications to the optimization procedure. A simple implementation causes the model to diverge right after the restart. Unlike basic stochastic gradient descent, which relies solely on the value of the gradient at the current optimization step, the atom update is primarily guided by the first and second moments of the gradient accumulated over previous steps. Assuming that at the reinitialization boundary, W_A and the corresponding gradient moments are full rank R, continuing to use old gradient moments for the new W_A will guide it in the same direction as the old W_A and optimize the same subspace. To address this issue, we propose ReLoRA. ReLoRA performs a partial reset of the optimizer state during the merge and restart process and sets the learning rate to 0 with a subsequent warm-up. Specifically, we set 99% of low-magnitude optimizer state values to 0 and use a jagged cosine learning rate schedule. Our studies show that both of these modifications are required to improve performance over the basic LoRA. In summary, ReLoRA is a low-rank training method inspired by LoRA that uses restarts to increase the effective rank of the update, uses a partial optimizer reset, and a jagged scheduler to stabilize training and warm starts. All of this allows ReLoRA to achieve performance comparable to full-rank training, especially in large transformer networks, by only training a small set of parameters at a time. Section summary. The method described in this section is called ReLoRA, which is a low-rank training method inspired by LoRA. ReLoRA utilizes restarts to increase the effective rank of the update, partial optimizer reset, and a jagged scheduler to stabilize training and warm starts. By training only a small set of parameters at a time, ReLoRA achieves performance comparable to full-rank training, particularly in large transformer networks. Section. Enhancing computational efficiency. We've developed a method to improve computational efficiency, which we call ReLoRA. Unlike other techniques that aim to reduce the complexity of training, ReLoRA keeps the original network's fixed weights and adds new parameters that can be adjusted. This might seem like it would slow things down, but it actually makes the fine-tuning process more efficient. The key is in the distinction between fixed and adjustable parameters. By reducing the size of the gradients and the optimizer states, we can significantly improve training time and memory efficiency. For instance, the memory used by the Atom optimizer is typically double that of the model weights. In addition, large networks often keep gradient accumulation buffers in 32-bit precision, which adds a lot to the memory used by gradients. ReLoRA reduces the number of adjustable parameters, which allows us to use larger batch sizes and make better use of hardware. It also cuts down on the bandwidth needed in distributed setups, which is often a bottleneck in large-scale training. Moreover, since the fixed parameters don't change between restarts, we can store them in a low-precision format, which further reduces their memory and computational impact. This extra optimization helps ReLoRA use memory and computational resources more efficiently, especially at scale. To test ReLoRA, we used it to train a transformer language model on the C4 dataset. We tried various model sizes: 60M, 130M, 250M, and 350M. Language modeling is a key task in machine learning, with applications in text and image classification, translation, programming, in-context learning, step-by-step reasoning, and many other areas. Because of its importance, we focused solely on language modeling for this paper. Our architecture is based on the transformer model and is similar to Llama. We used pre-normalization, RMS norm, Swiglu activations, a fully connected hidden state size of 8/3 times the size of the input, and rotary embeddings. We used bfloat16 for all floating point operations and flash attention for effective attention computation. Compared to Llama, which uses float32 for softmax computation, this increased training throughput by 50 to 100% without any training stability issues. Most of our models were trained on 8 RTX 4090 for 1 day or less. Due to computational constraints, we trained much smaller models than Llama, with the largest model having 350M parameters, the same as BERT large. We selected the number of pre-training tokens based on the chinchilla scaling laws for all models, except for the largest one, which we trained for 6.8 billion tokens, while 9.5 billion tokens would have been optimal according to chinchilla. Section summary. ReLoRA enhances computational efficiency by maintaining frozen weights of the original network and adding new trainable parameters, which reduces the size of gradients and optimizer states, allowing for larger batch sizes and reducing memory consumption. This approach also enables the use of low-precision quantized format for frozen parameters, further reducing memory and computational impact. In experiments, ReLoRA was applied to train a transformer language model on the C4 dataset, achieving increased training throughput and scalability. Section. ReLoRA and baseline setup. In our experiments involving low-rank training, we used ReLoRA to replace all attention and fully connected network parameters, while maintaining the full rank of the embeddings. The RMS norm parameterization was kept the same. Since models using ReLoRA have fewer parameters to train compared to full-rank training, we included a control baseline. This baseline is a full-rank transformer with the same number of parameters as ReLoRA. We started ReLoRA from a checkpoint of full-rank training at 5,000 update steps and reset it every 5,000 steps thereafter, 3 times in total. After each reset, we pruned 99% of the optimizer state based on magnitude and warmed up the loss for the next 100 iterations. We reinitialized ReLoRA parameters following LoRa best practices, using k-ming initialization for the A matrix and zeros for the B matrix. If we didn't use the restarts, we also used k-ming initialization for the B matrix to avoid issues with gradient symmetry. Our main results are presented in a table. ReLoRA significantly outperforms low-rank LoRa training, showing the effectiveness of our proposed modifications. Interestingly, ReLoRA performs similarly to full-rank training, and the performance gap decreases as the network size increases. The only model where ReLoRA didn't outperform the control baseline was our smallest model with 60 million parameters. This suggests that ReLoRA is particularly effective in improving the training of large networks, which aligns with our goal. To determine whether ReLoRA performs a higher rank update than LoRa, we plotted the singular value spectrum of the difference between the initial weights and the final weights for ReLoRA, LoRa, and full-rank training. The figure shows significant differences between LoRa and ReLoRA for the singular values of W_Q, W_K, W_V, and W_down. While most of the singular values for LoRa are 0 with a noticeable number of exceptionally high values above 1.5, ReLoRA shows a higher distribution mass between 0.1 and 1.0, similar to full-rank training. This emphasizes the importance of high-rank updates and shows the effectiveness of ReLoRA, which achieves a high-rank update by performing multiple low-rank updates. Section Summary. In our experiments, we replaced attention and fully connected network parameters with ReLoRA in low-rank training, while keeping the embeddings full rank. We also included a control baseline, which is a full-rank transformer with the same number of trainable parameters as ReLoRA. ReLoRA outperformed low-rank LoRa training and achieved similar performance to full-rank training, especially for larger networks. The singular value spectrum analysis showed that ReLoRA performs higher rank updates compared to LoRa, demonstrating its efficacy in achieving high-rank updates through multiple low-rank updates. Section 5.1 Ablation Studies. We've carried out detailed studies on the 4 key elements of ReLoRA: restarts, jagged schedule, optimizer resets, and warm starts, using a model of 130 million parameters. The findings are shown in a table. In this part, we'll concentrate on and examine certain combinations of these elements. Without the components mentioned above, ReLoRA is essentially the same as training a low-rank network using LoRa. This method results in a very high perplexity, suggesting that a simple matrix breakdown has a significantly different training dynamic compared to full-rank training. When we add restarts and optimizer resets to ReLoRA, but leave out the jagged schedule and optimizer reset, it performs similarly to LoRa. This is because the old optimizer states push the newly initialized parameters into the same subspace as the previous weights, which limits the model's capacity. However, if we simply reset the optimizer with ReLoRA, the model becomes unstable. A jagged schedule helps stabilize the training and positively affects the mixture. In our early tests, we noticed that a combination of a partial optimizer reset and a jagged schedule allows for a faster warm-up, as low as 50 steps, instead of the hundreds of steps needed when the optimizer is started from scratch. The warm start shows the most significant improvement, reducing perplexity by almost 10 points. To see if post-warm-up training contributes to the loss, we measured the perplexity of the warmed-up network, which was 27.03. This outperforms all low-rank methods except for our final ReLoRA recipe, but there's still a significant difference from the final network. This highlights the importance of early training, a concept similar to the lottery ticket hypothesis with rewinding. Section Summary. In this section, the authors conduct ablation studies on the components of ReLoRA, a model with restarts, jagged schedule, optimizer resets, and warm starts. They find that without these components, ReLoRA is similar to training a low-rank network using LoRa, but with significantly different training dynamics. Adding restarts and optimizer resets improves performance, while a jagged schedule stabilizes training. The most significant improvement comes from warm starting, which reduces perplexity by almost 10 points. Early training is crucial, similar to the concept of the lottery ticket hypothesis with rewinding.